can't beat the in-person interactions, the lunches, the dinners. The quality of the people that you meet over coffee here is just phenomenal.
Right, File.io for game developers, past, present, and future. Actually, it's File.io, past, present, and future. Although it is for game developers, it kind of is for everyone. Everyone here uses files, don't they? My name's Davidson. I am the head of engineering practice at Creative Assembly. Anyone here heard of Creative Assembly? Okay. Anyone here play Total War? Thank you. Thank you very much. It's great. I joined in 1999, so I've been there for 24 years. I wrote my first game in 1980 on an Acorn Atom, in Atom Basic. I'm a regular participant of this alphabet soup, which is the C++ committee. I'm also the chair of BSI IST5, which is the mirror group to the parent body of WG21, which is, of course, SC22, as you can see. But this is the group that standardizes programming languages and system software interfaces in the UK, the British Standards Institute. This makes me, in fact, the king of programming since the UK is a monarchy. So, kneel before me, all of you. I'm not going to make an independence joke. It's fine, don't worry. I started speaking at conferences in 2015. I tend to speak to 2 or 3 a year now, 2 or 3 a year, and I help organize and do all sorts of... I'm just a man about conferences, really. I deliver training at conference workshops. Anyone been to one of my talks before? Oh, blimey. Okay, excellent. Nice to see you. Thanks for coming back. It can't have been too terrible. Right, during the pandemic, I co-authored a book, Beautiful C++. It sold really well, actually. Thank you, everyone, for buying it. But your careers would all be greatly boosted if right now you were to buy 1 copy, maybe 2. Right now. Oh, yeah, hello.
Where at?
Where at? Anywhere you like. A bookshop. That's it. The foreword's by Bjarne and the afterwards by Herb, so I was quite pleased about that. I'm working on another book, The Game Developer's Guide to Learning C++. Goodness knows when it will see the light of day. I'm aiming at spring 25, but who knows. So the topic, File.io, past, present, and future. What I've done is I've broken the talk down into 5 questions. Why do we have files? What is a file system? Why should we avoid buffered file I.O.? How do we optimize unbuffered file I.O.? And how might the standard help us in future? So I'm going to divide the talk into 5 orthogonal sections to reveal answers to those questions. So we've got sub-megabyte days, more RAM, more disk capacity, moving data into and out of RAM, file I.O. in C++ from fstream down to the OS SDK, and the 64-bit address space. There's a fair amount of historic context and scene setting, which is basically the history of me and computers. I hope that's engaging and entertaining. And also, if you need me to slow down or speed up or speak up, do say this is your conference. You paid to come here, or somebody paid for you to come here. So do make sure that you enjoy it as best you can. Can anyone actually answer this question? Why do we have files? Okay, I've got a 40-minute talk here. Unless you guys speak. Yeah, go on.
Data needs to live somewhere.
Data needs to live somewhere. Sorry? Persistence. Okay. All right, good answers. All right, yeah?
We can't fit everything in RAM.
Oh, we can't fit everything in RAM. You've seen this presentation before, haven't you? Well, you check your... Did you stalk up to my room last night and check my... No. Good answer. All right, who knows what this is? Why on earth would you? It's a ZX81. Actually, who was writing code in the 2010s? Hands up, if you were writing code in the great. 2000s? 1990s? 1980s. Oh, here come the beards. 1985? 84, you're going to win this. Oh, no, 84, 83, 82. Right, gosh. I hate that question because I'm clearly getting old. Anyway, this is the ZX81. And when I started programming, this is what I started programming on. This was a machine I had at home rather than at my school. There was no storage attached to the motherboard at all. The CPU, a Z80, ran at a majestic 3.25 megahertz, which is 3 orders of magnitude slower than this beast. The machine boasted a kilobyte of RAM, 8 kilobytes of ROM, and that ROM contained a basic interpreter, a floating point calculator, and an operating system. Kids don't believe that nowadays. 8 kilobytes, 8 kilobytes, right? 8,192 bytes. You know, that's not a lot. And there were 2 ways of writing programs. You could either use the built-in basic interpreter and write quite simple things, or you could develop in Z80 assembly. It had a Z80 microprocessor. And you could push the envelope. And after 3 months of basic, I wanted to write an assembly. I wanted things to go fast. The workflow required me to use a thing called an assembler. And that would convert assembly instructions into a stream of bytes, okay, for the processor to consume. The bytes would consist of code and any data required to run the program, which was, in my case, usually a game. So this is the motherboard on the left-hand side. Bottom left, you'll see 3 3.5 millimeter sockets. One was for power. One was for power through a 3.5 millimeter socket. One was for input from cassette tape, and the other was for output to cassette tape. So once I've created this stream of bytes, I would insert a blank cassette tape into a cassette tape machine. Every household had one back in those days. And I press record, and I tell the machine to output that byte stream through the tape interface. And similarly, if I wanted to, I could load the byte stream back into the machine by saying, please load the byte stream, press play. The important thing here was that there was one stream of bytes. Okay? The entire program to be executed and the data to be used, all in one data stream. And it was extraordinarily painful. The standard of the tape medium was variable, as was the standard of the player or recorder. You could spend as much as you liked on a tape recorder. Most people didn't spend much money at all. And the control was out of reach of the machine itself, which is important. But it's what we had. It was cheap. It worked. This was my next machine, a ZX Spectrum. It had more color, more RAM, but still no machine-controllable offline storage. And it wasn't until here, the Atari ST, which I bought in 1987, that I first gained experience of files. Okay, this machine came with a built-in 3.5-inch floppy disk drive. Anyone here used a 3.5-inch floppy disk drive? Yeah, okay. It's a 3D print of this. What was that? Why don't you go home? Thanks, Tris. Nice question. Good question. Excellent question. I didn't have an Amiga because this had MIDI ports. Where was I? Right, a 3.5-inch floppy drive. There was 520 kilobytes of RAM on there, which was amazing. That was huge after being used to 1 and 16K. We still haven't reached 1 megabyte, by the way. You could upgrade it to a megabyte. But it came with a desktop. I suddenly needed to learn more about programming GUIs and things like that. But my focus remained on game development. The offline storage piqued my interest because until this point, I'd simply created my game as a long stream of bytes. And the user would read that into RAM and then transfer execution to a known starting point. The particular way that this worked on the Atari ST was interesting because what you do is you would insert a floppy disk into the drive, and that would notify the OS, which would then read sector 0, track 0, the first thing, and then it would see, oh, this contains a bootstrap program. I'll execute that, and then the game would load, and everything would be fine. Of course, this had some really severe implications for security and the spread of viruses, because all you had to do was insert a disk, and then the OS would say, great, let's run this, let's see what happens. Carnage, chaos, quite often. And another interesting thing about the floppy disk was that it could store 720 kilobytes. Okay, this was more data than the machine could contain at a mere 520K of RAM. That's why your answer was good. And at first I thought, wow, this means I can have more than one game on there. But in fact, as time went on, I realized I could do things like put more graphics on there, more sound, even different chunks of executable code specific to the game that I was, writing. And this is worth dwelling on briefly because I simply decided to swap code in and out of a running process because I could. Self-modifying code, in fact. And I was doing a lot of that back in the early days. Anyone here written self-modifying code? Oh, yes, you all look very ashamed of yourselves, don't you? Yeah. It's a parlous thing to do, really. That's an enormous amount of fun because code is just a special kind of data. And modifying code whilst it's running is just a special kind of data transformation. But it's not so strange now. We have DLLs in the Windows world. We have You can load and unload those whilst you're running a process. By the way, I'm a Windows programmer in general because I make games and games are developed on Windows. But also what I'm going to be talking about, it will work on Linux. How many Linux users, Clang, GCC, Kite, do we have here? Oh, really? Quite a lot. Okay. It's all relevant. Don't worry. Linux has got shared objects rather than DLLs. I think they're better than DLLs, actually. The mechanics of them are superior. But all of this is rather safer and more controlled than what I was doing. Just randomly changing bytes whilst the game's running. Never good. But so here we are, moving data into the game, into RAM, whilst the game is running, which is exciting stuff. How can I move it as quickly as possible? So there was, in fact, an entire book of a couple of hundred pages devoted to the Atari SF354 floppy disk drive. And I was able to completely understand the nature of the disk drive, the disk format, how data was stored on it, and I could try such tricks as customizing the formatting of the disk. Because ordinarily the disk would be formatted to 80 tracks with 9 sectors per track and 512 bytes per sector, but I wrote my own disk I/O software because I could. And so I could squeeze extra sectors onto the outer tracks. I could squeeze more tracks in if I was less tolerant. And I could even position where the tracks started, where the sector started on each track, and I could spiral 400 kilobytes of data from a 360 kilobyte surface in 9 seconds, which was faster than any game I saw, so I was quite pleased with that. But all of this reading of the hardware made me an extremely capable hacker and a pirate too. But it was acceptable in the 80s. It was fine. It wasn't illegal then. Now, a close look at what I'm describing here shows that only the medium has changed, because I've exchanged a long strip of magnetic cassette tape for a series of concentric rings on a magnetic floppy disk. There's an improvement in that it's machine controlled, it's random access, these are all nice things, and I can reasonably overwrite parts of RAM with other pieces of data from the disk while the game is running. But all of that is handled by me in my code with my slightly obsessive knowledge of how disk drives work. And my knowledge of where in the stream all the bits and pieces of the code, of the data that I'm interested in actually lie. But my workflow was really clunky. Every time I made a change to my program, I would have to reassemble the entire bit stream onto the disk, which wasn't necessarily a problem, but it was a bit error prone. I felt I could do better. And particularly, I wanted to be able to make changes to the bit stream on the disk while the game was running. And that wasn't really especially possible. And I realized at this point, this is what files are, aren't they? They're portions of the data stream on the disk. File names are bookmarks to these portions of the data stream. So I moved over to using separate files for the executable and the data during development, and I'd update them at runtime on my girlfriend's machine, because I had a girlfriend. I thought, hey, you'd like a computer, wouldn't you? Here, have a computer that's exactly like mine, and then we'll have 2 in the house, and that'll be really useful. Happy birthday. We've all done it. Oh, you stopped laughing then, didn't you? Right. I introduced a retail build step, which would dispense with all of this file searching, and it would rely on my knowledge of everything that was there, and I could write a single stream of data to the disk again. And I was still developing games in assembly language. The Atari ST sported a Motorola 68000 processor, so I was still very close to the metal. Now, I like to separate the sections of my talk with artworks. Think of them as commercial breaks. I also like to run quizzes. So I want the artist, the title, and the year. Who can tell me who the artist is? Anyone? Yes?
Fragmentation?
Sorry?
Fragmentation?
No. Anybody else? Yep. It is indeed Mondrian. Congratulations. Any ideas what the name of the piece is? It's composition 2 in red, blue, and yellow. You can see the red and the blue and the yellow on the composition there. Painted it in 1930. Mondrian is in fact an object-oriented version of the programming language Haskell. Anyone used that? Anyone used Haskell? And have any of you used Mondrian? That was a roaring success, wasn't it? Okay. It's also a web-based code review system written in Python by Guido van Rossum whilst he was at Google. Anyway, onwards. So I carried on writing games and honing my skills throughout my maths degree, which I did in the late 80s. And I got my first hard disk, 44 megabytes. Hello.
I'm curious, what kind of games they were at the time?
Very simple ones. At the time, there were all manner of games available, but history of games. I actually have an entire talk on the history of games, which I can point you to later. Or you can just button me in the bar and I'll bore you witless for 3 hours. Your choice.
What were you writing?
What was I writing? Well, nothing that got published. Well, actually, no, I contributed to games that got published, but most of the time I was writing, 2D, sprite-based games. We didn't have 3D hardware. Everything was done in software. There were no hardware renderers. It was basically, you had a frame buffer, and that was it. It's all yours, matey. Right to that, none of this hardware acceleration nonsense. I touch on this later. But once I got a hard disk, 44 megabytes of capacity, that changed how I did everything because suddenly I had so much data. I could store versions on there and all sorts. And my trusty Atari ST lasted until the summer of 1991 when I was burgled. All my kit, all my disks, all my backups, everything, because I didn't have an off-site backup. And it was a sad day. But my girlfriend had moved to a philosophy degree, and so she bought a Macintosh because, philosophy, Macintoshes, obviously. And I'd inherited her Atari ST that I so generously bought her for her birthday. And I started again with the insurance money, and then I was burgled again about a year later. I decided it was a cosmic hint that starting my own business as a game developer wasn't my destiny. So what I did was I secured a freelance role at an interactive media company called UCM, and I started using Windows on PCs with enormous amounts of memory, sometimes as much as 16 megabytes. 16 megabytes of RAM. I could live in that. I could take up a virtual existence. It'd be brilliant. And I came across Sandblaster cards, Wolfenstein 3D, which was, an extraordinary game. By this time, PCs were coming as standard with hard disk drives. And games were being released on multiple floppy disks that took advantage of the excessive capacity available to them. And the idea of a single stream of data at retail became impossibly hard to manage because everything got bigger, everything got larger. And some way of identifying and locating files became a necessity of development. Now, I'd already been using file systems, but I just hadn't recognized that that's what I was doing. I hadn't been very conscious about it. There were simply mechanisms by which you would slow down the operation of your game, only of use when you were looking for tools on your disks and loading them into memory. I fought against them because they slowed things down. The disk format natively supported by the Atari OS was actually FAT16, which was MS-DOS compatible. Back in those days, everyone was running MS-DOS. Even Windows users were running MS-DOS. Disks I prepared in my Atari, I could read from any PC anywhere. It was just the one file format. Anyone remember what you had to type to start Windows from a DOS prompt? No, that wasn't the answer I was looking for, although that is correct. The answer I was looking for was Win. Win! You want to run Windows? Win! That's the great gag. Right, FAT16 is actually short for File Allocation Table. And we'll get to the numbers in a moment. It was originally developed in 1977. The file system uses an index table. It identifies chains of storage areas associated with the file, and there's a whole hierarchy thing where you can say, this isn't a file, this is a subdirectory which contains more files. It's quite clever. Importantly, the table is immovable. The root directory is immovable. It's allocated at the time the disk is formatted. So it was very popular at the time. It was robust. If things went wrong, it could self-correct. There'd often be a second. Yeah, exactly. There'd be a second copy of the roots just in case things got messed up. The root directory of the disk contains the number of the first cluster of each of the files in that directory, and from there it works out where everything else is going. Each entry in the linked list is a fixed number of bits. So it's either 12 or 16 or 32, hence FAT16. And the more modern FAT32. Anyone here using FAT32? Is it still a thing? No, didn't think so. Gosh, I'm getting old. Now, my custom format that I was using for the Atari ST was completely incompatible with MS-DOS. Actually, it was completely incompatible with other Ataris. If you wanted to copy my disk, you'd have to read the bootstrap program and then disassemble it, work out what was going on, write your own encoder. It was very handy. It stopped all the piracy. But FAT16 is a disk format. That's the important thing. It's not a file system. We'll look at that next. All right, who's heard of POSIX? Yeah, just about everyone. So the Portable Operating System Interface POSIX is a family of standards specified by the IEEE Computer Society for maintaining compatibility between operating systems. POSIX defines both the system and user-level application programming interfaces, APIs, along with command line shells and utility interfaces for software compatibility, portability, with variants of Unix and other operating systems, including Windows. POSIX is also a trademark of the IEEE. POSIX is intended to be used by both application and system developers. Now, remember I said I was a delegate to SC22. POSIX falls within our purview. Part of the POSIX specification is the file system. So for a file system to be compatible with POSIX, it must implement strong consistency, it must have atomic writes, it must implement certain operations, reads, writes, truncate, that sort of thing. And it's got to control access to files. Okay? So let's look at the C runtime library in this context. We've got file access, we've got direct I/O, we've got unformatted I/O, we've got formatted I/O, we have file positioning, telling, getting, seeking, and we have operations on files. So when I first discovered the C file I/O library, there were two problems for me. How do I move bitmap data into RAM? And how do I find files? Now, when C was getting into its stride, the world of computers was text-based. So fun fact, in 1974, Evans and Sutherland released the first commercial frame buffer. It cost $15,000. You might think an NVIDIA 3090 is a lot of money, but it's not a lot of money. $15,000 in 1974 is a lot of money. And it was capable of producing resolutions of up to 512 by 512 pixels using 8 levels of grayscale. And I know that's a color picture. I could have put it through Photoshop and grayscaled it, but I didn't. So I'd like you to imagine it's grayscale, okay? Just for me right now. Everything back in the 70s was text. Everything. Formatted I/O would insert values into strings. Unformatted I/O would put characters into a character array. And direct I/O would read n bytes into a void star buffer. And if we look at these APIs, you can see they all have something in common, a file star parameter. More on that later. So how did I find files? I had to fall back onto the OS. Okay. One thing a file system should expose is an API for selecting files and enabling reading and writing. C does not have one of those, although C++ since 2017 does. The file system library is pretty comprehensive. It deals with files, names, and paths. It differentiates files between directories, links, block files, all of that malarkey, and it accommodates special file names like dot and dot, and it's got a full command of the vagaries of paths, including optional root names, absolute and canonical. It's brilliant. You can iterate through directories. You can find out how much space you've got in your file system. You can copy files, create directories, get files. I wish I'd had this back in the 1990s, really. But this is the file system, though. It's not the format of the file system on disk. Now, I remarked earlier that I started off using FAT16, which was MS-DOS compatible. The file system was defined by MS-DOS, while the disk format was defined by FAT16. Now, this separation is important because they often get mixed up. Anyone familiar with Riser FS in the bottom right? It's a great piece of work, although, unfortunately, the developer is currently incarcerated. For pretty good reasons, to be frank. But you can see that your application makes system calls to communicate to the Linux kernel. Okay? POSIX defines the behavior of these systems calls, and the VFS runtime, the VFS handles all the file system-related system calls. And this abstracts from the underlying file system. There's the important bit. It's the abstraction. So if your file system developer suddenly becomes unavailable, you can simply swap in another one. And POSIX is great here because you can swap around file systems, and it doesn't matter. As long as there's a driver that the VFS can use to deal with all of the calls from Linux, then we're all good. And I should point out that Linux is only partially POSIX compatible, as far as I can see, because reads and writes are atomic on a page level, but a read might return some pages of a concurrent write operation. But it seems to be good enough for everybody. So POSIX was developed for local file systems. Okay, all sorts of guarantees are available to you when you own a piece of hardware. And the thing is, POSIX has been so fantastically successful that it's been the expected API for other file system solutions, like distributed file systems. And what we seem to want from distributed file systems is the presentation of the typical file system API. But with the opportunity to simply add more storage volumes as necessary, I'd love that, but it's not going to work. Many have tried. I went to Wikipedia. I looked at a comparison of distributed file systems, and many of them, particularly the proprietary ones that you pay tens of thousands of dollars for, offer POSIX as one of the access APIs. I dread to think what's going on under the hood there because, well, I spent a chunk of 2022 giving talks about abstraction. And if you aren't familiar with the idea of abstraction, Go and view one of those talks. I'm recommending the C++ on C iteration. Is Phil here? Phil Nash? No, he's got better things to do with his life, hasn't he? All right, it's Phil Nash's conference. It's a great conference, do go. And that's the one I like. There'll be a link later, really. The reason I remark on this is that I believe that there is an abstraction problem going on here with the idea of trying to put a POSIX API on top of a distributed file system, because POSIX abstracts the complexity of managing multiple processes, requesting I/O services from local storage. That's what's going on there. It's the local storage. Distributed file systems have additional complexities which need to be abstracted. What happens when a device is temporarily unavailable? Or when data takes much longer to arrive than you're expecting? Or when multiple processors on multiple machines want access to the same file? How do you broker all of that? And that seems like a horrendous task to navigate inside of POSIX. File system is a word that does a lot of heavy lifting. One of the reasons that cloud computing has become so successful is because it offers a better abstraction for the problem of distributed storage, without pretending to be actually a general purpose file system. All right, artist, title, year? Artist, anyone? Yes, congratulations. Any idea what the piece is called? It's called Impression, Sunrise, full stop. Who's heard of Impressionism? Yes, that's the piece that's launched Impressionism. He painted it in 1872. The painting that gave us, there is a database management system called MonetDB, which I found peculiar. There's also multi-wavelength optical networking. Multi-wavelength optical networking, Monet, there we are. It's a method of digital fiber optic communication. All right, I'm starting to rush because I'm taking too long on this. So we've now got a way of finding our way to the bits on or within the storage device. How do we actually get that into RAM? Okay, so now's a good time to remind everyone how long things take, because the answer is very long. I hope you're all familiar with cache levels. Everyone knows that caches exist, and so when I started programming, there were no caches. No caches, just, I want some data. There it is in RAM. All right, get it from RAM, put it onto the processor. But now we've got level 1, 2, and 3 cache that resides on the CPU. Actually, in another of my talks, I discussed how the whole of computing is basically getting data to and from the CPU to various places, into cache, into RAM, onto external storage, over the network, and how data is stored in caches to speed up the transfer as necessary. Right, this is an Intel CPU. Any Intel CPU made in the last 30 years will have a memory management unit on it. Now, this moves memory between RAM and the level 3 cache. Now, conceptually, RAM is just another level of cache, really. It's just a bit further away from the CPU. And you can think of all of these different storage mechanisms as different levels of cache. You can give them kind of equivalent level behavior. All of the devices, NVMe drives, SSD drives, disk drives, all of these things are connected to the motherboard. RAM is connected to the motherboard. It's controlled by hardware local to the system. Now, the drives obviously store data even when the power is off, and the cost of this convenience is that it takes quite a while, relatively speaking, to move data to the CPU, because first it needs to move it to RAM, and that's the bit that's time-consuming. All of these devices are connected to the motherboard by a serial bus, and there's a world of difference between quoted bandwidth and what you'll see in typical applications. Consider what goes on under the hood during a typical fopen, fread, and fclose operation. So here's the fopen file signature. It creates a file object for you, and it uses that file object to hold a buffer to the file that you're opening. Okay? How big is that buffer? Well, if you're on Linux, the macro buffsiz will tell you. And it's buffsiz, it's not buff size. Please don't say buff size at me, it's buffsiz. There's no E in that. It's usually about 4 kilobytes, all right? And you can use the set vbuff function to change the buffer size if you're working with particularly large files. When you call fread, the C runtime will ask the kernel to read some data into memory owned by the kernel and then copy it to your file buffer. And so from there, you can copy it to wherever you like. There's a lot of copying going on. And it might seem a little suboptimal, but consider what the rest of the API offers you, because you can get individual characters, you can scan for runtime formatted data. These are all useful things, because what's actually happening is that the C runtime is caching data for you in the file buffer and maintaining pointers to the beginning and the end of the buffer, and keeping track of where you are in the file itself is doing a lot of the work, the business of navigating your way around a file. And the amount of time to perform that extra copy compared to the amount of time to move from storage into RAM is absolutely tiny, isn't it? Still, you might expect C++ to offer faster operations. Let's take a look. So now, instead of creating and managing a file object, we're managing a stream of data. We have the class fstream, which also has some really nice insertion and extraction operators, which you can see here match up with the get and put functions of the C file IO library. Now, last time I checked, and this was 15 years ago, I should point out, I probably should have checked before I wrote this talk, but I'm sure it hasn't changed. The MSVC fstream library, the Microsoft fstream library, was actually implemented in terms of the C file IO library. And there's a good reason for this, because the C++ streams library was a product of the 80s. You know, it's a great model of design for the period, showing off multiple inheritance, virtual inheritance, good abstraction, an easier to use API, all those sorts of things. But it's still a product of an era where file sizes might exceed the available RAM of a machine. Okay? And the important thing for a file IO API to do then was to move a cursor around a file and move chunks of the file into RAM. Database tables, for example, they might contain millions of records, and whether they were on a tape or a disk, the job of the code is to read selected records into RAM and then make decisions based on their content. So let's look at this struct. It models a record of a member of staff. So pop quiz, one of my favorite interview questions: how big is this struct? Yes. So none of you are interviewing for a job, so you can safely remain silent without fear of embarrassing yourself. The correct answer, of course, is it depends. Okay? Here's a clue. Time t is an implementation-defined type capable of representing time. Although not defined, this is almost always an integral value, holding the number of seconds, not counting leap seconds. I came across it there once, since January the 1st, 1970, UTC, midnight. That's POSIX time. We're 53 years in. We're very close to 1.7 billion seconds. Billion. That's a big number. Can we agree on 84 bytes, 64 for the chars, 2 ints for the time, 3 ints for the rest? Okay? No, we can't, because what I didn't tell you is it's 1974. And in 1974, on this platform, an int is 16 bits. A char is 7 bits, but stored in a single 8-byte value. Time t is a 32-bit value because, honestly, by 2038, we'll be using something different, or otherwise we'll have much bigger problems to solve. I'm sure there's an XKCD comic about that. I couldn't find it, but I'm sure it's there. If anyone knows what it is, do tell me, because I'm not spooling through 2,000 comics just to find one. But the giveaway was ID high and ID low, because you really don't need 18 quintillion staff members, which is what you would get from two 32-bit values. But you probably need more than 65,000, though, especially if you're the government. Also, in 1974, people weren't on the payroll for more than 60,000 of anything. Enough of this. It's 1974. The size of this struct is 74 bytes. So the code that we need to read a record, it looks like this. So I want to read my buffer, which is likely an array of staff member objects. 10 staff member objects from the file I opened a little while ago. Of course, this will also compile. Not only will it compile, it will also yield the required behavior, and that annoys me more than seems reasonable. And notice also I wrote size of staff member. This is future-proofing, because if you recompile this today, int is larger, time t is larger. Anyone remember the 2038 epoch bug? Started showing up in 2006. Also known as the epocalypse. It was a few years after the Millennium Bug. Anyone remember the Millennium Bug? Everyone absolutely lost their minds over this. It was extraordinary. So the problem was that Unix, or POSIX actually, showed no signs of waning popularity, and we're going to be stuck with it. And after the horrors of the Millennium Bug were avoided, the computing world swung its gaze to Unix and decided that providing a solution 30 years ahead of time, rather than 3, was probably the right thing to do. So one of the problems we have with our file IO API is that we have all sorts of places where we're tempted to encode the size of a thing as an integer, rather than calculate the size according to the supplied implementation. So this isn't restricted to reading data either. The corresponding write API is similarly trap-laden. We're extracting and inserting data with these operations. So how does C++ help us write better interfaces? Well, operator overloading comes to the rescue. We've got these beauties. Basically, I'm sure you've all seen them. Now the type is embedded in the API rather than some terrifying void pointer, and we can write safer code. What do you call these operators? Does anybody have a pet name for them? I'm just curious, because apparently I'm a little unusual. I name them by what they are rather than what they do. So this is a chevron operator, left and right chevron, which in this context is used for inserting and extracting to a stream. But also I've written game where the chevron operator was used to add units to add soldiers to a unit. Because I write games featuring featuring squadrons. This is the parenthesis operator. It is not the function call operator. Your overload may not call a function, although that'll be a bit unusual. This one's tricky because the symbols are actually brackets. But there are those who name parentheses brackets. It's usually used for index or subscripting. We've seen all this before. But there's no requirement for that to be the case. I've heard this called the square operator. Naming is hard. I have to say that in every talk, that naming is hard, because it is. But now we've got the chevron operator for inserting and extracting from a stream of data, and this is delightful, it's safe, it's readable. We can spool through a file in chunks according to the size of the buffer defined by the runtime. We can safely read and write as needed. Everything's lovely. But there's still quite a lot of work going on. There's a lot of work going on. It's worth your time single-stepping your way through a function call and seeing how much code gets called, because you're not just reading a byte into a file, you're reading a byte to a buffer which represents a window into the file. There's bookkeeping to be done. What happens when you overrun the window? Your thread will block while the kernel gets the next piece of data. It seems that we can do better than this, because we're in the modern era. We've got machines toting 16 gigabytes of RAM as standard, and the idea of carefully spoon-feeding files in 4 kilobyte chunks into RAM is surely no longer appropriate. Why doesn't C++ offer any alternatives, like read this entire file into RAM right now, please? And the most obvious answer is that there are a world of machines out there deploying C++. This is an Arduino. Who's heard of a freestanding implementation? Okay, so a freestanding implementation, it looks like you're all C++ standards people. So, okay, freestanding implementation is important. Look up Ben Craig. He's the man to talk to about freestanding. People like me write software against an SDK, like Win32, where the operating system provides a load of services. But embedded systems, like the Arduino, they don't usually have those fripperies and niceties. They often have very limited amounts of RAM, and the very idea of dynamic allocation is enough to send implementers into a frenzy of panic. So in my day job, I rely on the Windows SDK to read large files into RAM, unbuffered and fast. Right, artist title year? I never know what pieces of art are famous that everyone knows, apart from things like the Mona Lisa. Okay, this is Ingres, Jean-Auguste Dominique Ingres. It's Romulus' victory over Akron, 1812. And of course, Ingres is a database. Anyone use the Ingres database? Oh, so very 90s. Okay. And there's also Ingres paper, which is a type of drawing paper. Right. Let's start at the top with fstream, which is described, is implemented in terms of file style. I work on Windows for my day job, so the code would look like this. fopen is implemented in terms of create file on my implementation. So that's how it works. But are we finished? I've still got 20 minutes to go, so clearly not. Things are about to get a lot more interesting. So in 1982, Intel started work on the 386. They released it in 1985. And it represented a big step forward in the evolution of the x86 architecture. Now, this memory management unit that I alluded to earlier also introduced something called a virtual mode. And up to this point, the architecture had worked with what's called a segmented architecture, which hopefully none of you know about, and none of you ever had any experience of using because it was extraordinarily painful. But once we had the MMU, we just had this flat area of memory. We could address everything with a single number. It made it much easier to implement operating systems that used virtual memory, because extending the architecture into 32 bits made it possible to address 4 gigabytes of memory without having to worry about segment offsets. You'd have one register which would say, oh, we're about here, and then another register which would say, actually, to be precise, we're a further 17 bytes in from that location or something like that. there was this complex dance with pairs of registers. It still gives me nightmares. Now, the virtual mode made it possible to run one or more real mode programs in a protected environment. So this meant that, okay, when you were running Windows on a 286 processor, you'd start your computer, run Windows by typing Win, you'd double click on an icon, and you start on your executable, and if it crashed, the entire computer crashed. That was it. Bang, bye, gone. And it was time to reboot. Bad times. Running Windows on a 386 processor, in enhanced mode by typing Win/3, provided access to the virtual memory capability of the processor. Windows applications can use more memory than is physically available. And like if one of them crashed, it didn't take everything down. It was just that individual process that would crash. It was great. This is the Strahov Abbey Library in Prague, by the way, which is amazing and beautiful. More memory than is physically available is a bit of a strange phrase. And it was done by swapping between RAM and external storage. You've seen this happen, I'm sure. So RAM that has not been accessed recently could be swapped onto the hard drive, and the RAM left behind is repurposed to another process. That's how swapping works, and all via the magic of an on-chip memory management unit and a willing and cooperative operating system. So I'm not going into the details of how this works. That's for the 90-minute version of this talk, which I'll be writing shortly, I'm sure. Each process, though, has its own 4 gigabytes of address space, okay? Regardless of how much RAM is available. And that address space is broken up into contiguous 4 kilobyte pages. There's that number again, 4 kilobytes. As those pages are used, they're written to RAM, and if there's no RAM left, another process that hasn't been used for a while will have its RAM evicted, and then the OS will map process addresses to sectors of the storage device. That's amazing. Windows programs, for example, contain several system DLLs in the process address space. Another thing you can do is map different process addresses to the same sectors of your storage device. So you can have a file that's shared between multiple processes. So you only need to load one copy of it. And it's being loaded read-only, so no processes can actually muck around with it. It's stable for all the processes. One of the properties of this mapping process is whether or not the file is read-only. You know, if it's read-write, then you can write to that address and it will flush to the hard drive. We can take this a step further. We can map arbitrary files to arbitrary process address spaces. So this is a heavenly advance in the status quo ante, to be honest, because rather than open a file and block while it's read to a kernel buffer and the portion you're interested in is copied to your buffer, you can simply map the file into your process space and access it as normal. There's no more sort of reading and writing going on. Of course, first access to any page of this address space will still result in a block as the data is read into RAM, but it's unbuffered, which means there are savings of RAM and memory copying. These savings become more significant, as we'll go into shortly. And not only that, but if you're in the habit of only using part of a file, for example, if you're using mipmaps, you'll only actually use one little bit of the file, you don't need to read the whole file in. You just read the header, and then you read the bit of the file that you want, and that's the only file I/O that will take place. You don't need to carry out multiple read instructions, you don't need the bookkeeping, you just simply access the address you're interested in, and you endure the blocking that you would have endured anyway. And you can map the file on one thread and read the file on another thread by touching addresses at 4 kilobyte intervals. The moment you know that you're going to need a particular file, you can map it, instruct your touch thread to do the touching, and once you actually need to access the file, with any luck and sufficient advance warning, you'll suffer no blocking at all. And if you try and read the file on your working thread, it will block as normal anyway if your other reading thread hasn't reached it. But that's no worse than what was going to happen anyway. You know, there's no losses here. The API is slightly more involved than the create file, read file pair. This is Windows, obviously, it looks like this. But you'll notice this is only 3 lines of code. In the prior example, you had to define your own buffer. But we've already got the file. We don't need a buffer. But there are a lot more parameters to worry about. You can see an absolute slew of them. And this is abstraction writ large, really. The highest level of abstraction offers the simplest API. As we delve deeper into the OS, things become more complex. Now, I'm making a massive assumption here, but I'm guessing that the create file, read file system works by mapping the file into the process and then copying to the buffer of your specification, just like fread. Without this buffer copy, we have unbuffered file I/O, and the kernel delegates all the bookkeeping to the memory management unit on the chip Now, there's an additional problem because modern processors have caches, instruction caches, data caches, and they're all copies of RAM. So the value of caches is that accessing the memory takes a long time. So when you address a piece of RAM, it's a smart move to simply get a big chunk of it and just keep it to hand for the next operation, which is likely to take place on the next byte of RAM, locality of reference. And all of this is made possible by the memory management unit. The assumption is that all changes to RAM are brokered by that unit. You need to be completely aware of all changes to RAM so that you can update the cache. Anyone here heard of DMA? Yeah, great, good. This is the thing we used to do ages ago. Direct memory access enabled you to tell a disk drive to put data into RAM without bothering the CPU, except to notify when the transfer had finished. And it was an early kind of threaded I/O, leaving the CPU free to carry out more important work rather than blocking on external hardware. But unfortunately, with all RAM updates now being brokered by the on-chip memory management unit, it's no longer available to us. I suppose a read thread is a kind of DMA, but even then, you're still nudging the CPU. We'll come on to a better type that's starting to emerge shortly there. All right, last one. Who's the artist? Leonardo da Vinci. Go on. Yeah, you're right. Don't be alarmed. It is Leonardo da Vinci. Who can name this piece of art? The Last Supper. Who can give me the decade it was painted in? It was the 1490s. He painted it, between about 1492 and... It took him a few years anyway. Great biographies of Da Vinci exist. They're all worth reading. I don't know what it is about people who write biographies of Da Vinci, but they're all slightly nuts, just much like the man himself. Texas Instruments Da Vinci is a system on a chip for digital video. Da Vinci, digital video. There we are. The Da Vinci machine is a project to add dynamic language support to the Java virtual machine. I have no idea what state it's in right now. There's the Da Vinci project, which is a suborbital crewed spacecraft. And then there's Da Vinci, all in uppercase, which is a planned NASA mission that will send an atmospheric probe to Venus. That's going to be exciting and hot. All right, things have got proper huge now. Storage is huge. I can buy a couple of terabytes of NVMe for the price of a night out. 64 gigabytes of RAM cost me about the same. Files, on the other hand, have not grown at the same rate, at least not in my line of work. Okay? I rarely need to extract portions of files. I just need to load textures or models or audio waves or video clips. I'm good to go. Why has C++ not caught up with this? Okay, so I want to close the talk by considering 3 potential arrivals coming to C++. The first of these is hash embed. Anyone heard of hash embed? Ooh, good. It started life as a proposal written by Jean Manida for consideration by the C++ committee, P1040. Does everyone know about WG Link? If you want to, if you want to keep on top of the C++ standard, go to WG Link. WG21.link. What's it called? I don't even know what it's called. It just automatically falls out of my fingers. Go to WG21.link, and it will give you papers and all sorts of things about the progress of the standard. But the abstract is very simple. A proposal for a function that allows pulling resources at compile time into a program. What if I could store all my resources in the binary rather than externally in a file system, like I did 40 years ago, when everything was brilliant? My heart leapt for joy. And the first example looked like this. Okay? So you can imagine there should be a stud in front of the embed, and there should be a stud in front of the span. It's slideware, but you can see what's going on here. Now, the paper went round the houses in the C++ committee, but it didn't gain the necessary traction because one of the biggest problems was dependency scanning. And rather than grind through the issue, John Heed said, all right, I'll go to the C committee, see what they think. So the proposal N3017, they do things differently there. They don't have WG21.link. But rather than creating a library feature, the proposal is that hash embed be a preprocessor directive, like hash include, but for binary data. So this was a popular position. It was so popular, the committee was mailed a physical letter of support from an engineer at DMG Mori, Japan. He actually typed a letter and he signed it with ink. Fantastic. So now the example looks like this, but of course it's C, so there's no const exp. But it's easy to envisage a const exp value being used by a const exp function to perform compile time computation that would have been performed at startup or during runtime. Const expert, all the things. Well, nearly all. I have some reservations. So please contact your implementation vendors, request they bump the priority of implementing hash embed just for me, please. I'd be very grateful. It would make me very happy. And if you'd like to read about how hard it was to get this blindingly obvious feature into the C standard, Jean Heed vents entertainingly at that address. It's a great read. If you're an MSVC user, I've opened a developer community issue at this address. Here's a QR code. I can wait. Yes, thank you, yes, lovely. Right, next we'll take a look at a paper by Niall Douglas. This is 1041, and it's a huge beast. No, 1031. It's a huge beast of a paper. It's attempting to propose an entire low-level file I/O library to supersede I/O streams, and it's a valuable paper in that it shows how much has changed since the I/O streams library was delivered to the programming public. Back then, obviously, spinning Rust was the name of the game. A randomly placed 4 kilobyte I/O to RAM takes up to 5 microseconds, but while to a hard drive, using perpendicular magnetic recording, which was the premier technology of the 80s, it's more like 26,000 microseconds. So the usability cost of the I/O stream library was utterly dwarfed by the cost of disk I/O operations. A SATA-connected flash drive takes maybe 800 microseconds, but it's also highly concurrent. It can service between 16 and 32 random 4 kilobyte I/Os at the same time it would take to service one. And doing the arithmetic on a SATA-connected flash SSD with queue depth of about 32 I/O, every unnecessary memory copy increases I/O cost by a minimum of 20%. Don't buffer your I/O. When we start taking NVMe into consideration, we're looking at 300 microseconds rather than 800. This is only going to improve, and the decision to use buffered file I/O for I/O streams is going to become more costly. The paper is too large for the committee to review as a whole, unfortunately. It's a magnificent piece of work. So the way ahead is to break it into its constituent parts and introduce those instead. So next we'll take a look at P1883, stood file handle, and stood mapped file handle. And in revision 2, he offers all the furniture required to standardize file mapping. Now, remember earlier I was talking about the Windows SDK to optimize my file I/O. The obvious problem with that is that it's non-portable. And if I'm writing for Windows and Xbox and PlayStation, I need to learn how each platform supports this feature, what each API looks like, what its foibles and functionality differences are. And this is exactly why standardization is a good and necessary thing. Okay? This is a CPU feature, and it's part of the POSIX standard as well as the Windows SDK. I'm not going to tour through the proposal. It's 53 pages long. And while it's a well-written piece of work and a cracking read, it's still speculative, and it's beyond the scope of this talk, but I do recommend sit down, get a pot of tea, and study it after you've digested his earlier paper, because you'll learn a lot about file I/O. I certainly did. And be ready for this feature when it finally lands. If efficient file I/O concerns you as much as it concerns me, and game players don't like loading screens, they really, really don't. It breaks the flow dramatically. Then you can do yourself a massive favor by contacting Niall with words of support and ask how you can help him, because even if this proposal doesn't form the basis of I/O Streams v2, something needs to be done. I'm too busy with linear algebra at the moment, otherwise I'd probably take a look. I might take a look once I've got linear algebra out the door. But one place the standard won't help us for a while is DMA, but Windows is giving it a good go with direct storage. Anyone used direct storage? It's a bit niche. No. Okay, so what this does, this migrates data across the PCI bus. So you put an NVMe drive on your PCI bus, you put a graphics card on your PCI bus, and you just move data from the NVMe to the graphics card, and you don't touch RAM. You don't bother the CPU at all. It's fabulous. It's absolutely fabulous. At the moment, you need Windows 11. You need a GeForce 1390. This is not cheap hardware. But as cards start to support direct storage, you can expect to see game load times drop quite dramatically as textures skip RAM and CPU time entirely. So we have files because a typical program cannot contain all the data it needs. Either there is insufficient RAM or insufficient address space, or there is too much data. Or maybe the data isn't ready at compile time. It's supplied at runtime by the user of the machine. A file system is a way of organizing files such they can be easily accessed via some identification system. Bits distributed across an SSD are organized by a file system that describes the start and end of a file. A file system is a series of bookmarks into the storage medium with handy search facilities. We should avoid buffered file I/O because it is expensive, unnecessarily so. Taking the whole amount of time required to move some data from an external storage medium to your program, the percentage of that which is simply moving memory from buffer to buffer is increasing as storage technology improves. We optimize unbuffered file I/O by using the information that we have at hand. Okay? When we know we're going to need a file, we map it immediately and start touching it on another thread. We're able to read the file if we need its data before our touch thread has reached that data. No losses at all. This standard will help us in the future by supplying a new version of IO Stream in the fullness of time, and by eliminating the need for files in a few places via the new preprocessor directive, hash embed. Combined with const expr, this will reduce runtime computation. So here are some useful links. Please ask me 2 questions. Thank you very much. There's the microphone. Excellent.
Thanks a lot. Great talk.
Thank you, thank you, thank you.
So you mentioned the hash embed.
Yes.
And basically that it sort of like takes us a few decades back. So I would imagine, we'll have a const expr unordered map, which is the file system to point into the different buffers and embed. How will that work?
I don't know. Be brilliant though, won't it? The thing is, this is why we need to see it. We need to start using it. We need to see how it's going to work. We need to iron out all these things. Now, this is why I'm saying, please contact your vendors, get them to implement hash embed. It's going to become, really important. We've spent 4 decades mucking about, moving files in and out of RAM, like it's normal, like it's a thing. I was programming for 8 years before I suddenly went, "Ooh, files. What are these? This is exotic." So, great question. I don't know. Let's start playing. This is the great thing about C++. New features come along and we think, "Oh, what does this do? This is brilliant." That's where it needs to be. Any more questions? Ooh, trot, trot. No, you're leaving. Oh, okay. You're dead to me. Oh, no. No. Here's a question. Oh, brilliant. Thank you. Sorry, I do apologize. You're a very lovely man. Thank you.
Right. So memory mapping is a great technology for quickly paging in the exact information you need. One of the drawbacks of it, though, that we found, at least on the Windows platform, is that when you go to memory map a file, you actually have to reserve the entire address space for that file, and the OS will commit that for you. So your program is just going to use tons of memory if you map lots and lots of files.
It's going to use tons of address space. It won't use tons of RAM.
Yeah. And up front, of course, regardless of if you use the entire file. So is this something, how do you balance that?
Well, to be honest, I haven't come across a situation where I've needed to balance it yet because of the nature of the programs that I write. You are, of course, correct. There are, of course, downsides. You've actually got to do all the bookkeeping to work out where all the sectors are that correspond to the address space. I don't have a magic bullet answer for that. But like all things, engineering is a set of trade-offs that one has to keep. But thank you for keeping me honest. Yep. That is an absolutely valid question. And if you've got any data that comes up about where things start to become treacly, I would be very interested to hear that.
After the talk.
Absolutely. Let's do that. Any more? Thank you.
So,
One more.
So you mentioned the POSIX.
Yes.
And at least from my old experience, Windows and POSIX didn't go very well together. And I think that was maybe a root cause why standardization of a language was hard, because you had to basically try to find a common ground between different OSs. So I wonder if there's any direction to get everyone on board on something. And
that's above my pay grade. I'm WG21. I turn up at SC22 meetings and go, "Oh, okay." I can't answer that question. I don't know.
Okay, and on a similar note, maybe we should standardize the cloud-based object stores as well.
Well, that's probably out of the scope of C++. C++, you're writing stuff that will, you're writing stuff for the CPU. And we're starting to look at the GPU and think, well, C++ on GPU, maybe that's the thing we can start standardizing. But I think standardizing cloud stuff, that's for a different standardization body. I'll bet there is one. There's millions of them. A different standardization body could work on that. We've got three large companies competing to be the cloud provider. I think eventually it's going to happen. It's going to be a Betamax VHS situation.
But at least like RESTful type get put things that work for S3 and others.
Yeah, RESTful. Maybe. I don't know. I make games. I don't really use the cloud very much. I just know it exists. Right, time to go. Thank you all very much.